Hey everybody, welcome back to another lecture video. This time we are looking at chapter 15 on chirality. So let's just get right in and start talking about what it means to be chiral, or how we determine the chirality or handedness of a molecule. Now we've talked about isomers before, and in this chapter we're going to study enantiomers and diastereomers. So we've looked at how isomers can have the same molecular formula, and that if they're connected differently, they're constitutional isomers. So, for example, some alcohols and ethers have the same formulas but are connected differently. If they have the same connectivity, like our cis and trans molecules that we looked at, then they're stereoisomers. Now, or they're a type of the stereoisomers. Now, of the types of stereoisomers, there are the kind that have stereocenters, and the kind that don't have stereocenters. The without stereocenters are called achiral, and with stereocenters are called chiral. So the chiral here is talking about a stereocenter, a place where, depending on your orientation, you end up with some isomers. A stereo without a stereocenter, so that means, well, I guess we have to define what a stereocenter is. A carbon is going to be tetrahedral, or bonded to 4 different groups. Okay? That is a stereocenter. When a carbon has 4 groups that are unique, if 2 of those groups are the same, then it's not a stereocenter. And this has to do with the way that we can orient a molecule, and I'll show you some examples here in a second. So we're going to be looking for chiral, we're going to be looking for carbons, and we're going to be looking for carbons that have different groups on them. If they have different groups, then we'll end up with either enantiomers or diastereomers, and so we'll have to talk about the difference. If there is no chiral center, then that is like our cis-trans isomers. And right off the bat, you can see by my definition of 4 unique groups that a double bonded item like this that does have a cis or a trans being separate from it being a different molecule. It's the same molecule, same connectivity, it's just different orientation in space. The Cl is down in this one and it's up in this one because this double bond cannot rotate. But if it could, we could see that it would put the H back up and the Cl back down if it could just turn, and then it would be the same. These have no stereocenter. The carbon here has 2 bonds to carbon. It needs to have 4 unique bonds for it to be a chiral molecule. So let's take a look at enantiomers. Now, enantiomers are non-superimposable mirror images. So molecules can be mirror images of each other, just like your hands are mirror images of each other, but superimposable mirror images. So this just means that they're not the same molecule. And so here I'll try to illustrate that. If we take a look at this molecule here, we can see the original molecule in the mirror image. It should be mirror images. This carbon here, for example, is this carbon here. CH3 on the end, CH3 on the end. These 2 hydrogens are facing us. These 2 are facing us as opposed to away. It's a mirror image. Let's take a look at if this is a chiral molecule. So we've got a carbon here that has an OH group, a methyl group, a hydrogen, and an ethyl group. Any other carbon in here does not have 4 groups. Just taking a look at any other carbon and we see that. This carbon, for example, has 3 hydrogens on it. So 4 unique groups is already violated. CH2 or CH3, like we just said, multiple H's, you're not chiral. So every time we have one of these chiral carbons, we introduce a place where we could have an stereoisomer. Let me show you why these are not superimposable. To be able to see why the mirror image of 2-butanol is not superimposable, let's rotate it. So this is the same molecule as before, only, yeah, same as before. Only not in the ball and stick model. So if we were to take this guy and rotate it, okay, so spinning it around 180 degrees, so that these groups down here all change, they'll rotate, right? So we're going to get so if we move this 180 degrees, we're going to get this group on the other side and these two groups, right? They're going to switch. Their positions also flip. So the methyl here, this is in line with our plane. That's going to stay in line with our plane. But the other two were sticking out at angles. The H was going back into the distance of this screen, and the ethyl was coming out at us in the screen. So these have to flip. So now the methyl is going back into the screen, I'm sorry, the ethyl, and the hydrogen is coming out at us if we flip this thing around. Now let's compare these two molecules, and we can see that the ethyl and the hydrogen are in the wrong places. The OH is in the same spot, the CH3 is in the same spot, but we have the ethyl going backwards here and the hydrogen going backwards here. That means if we put these on top of each other, the ethyls wouldn't line up, the hydrogens wouldn't line up. That's what superimposable means. So these are not superimposable. All right. Now, a molecule that is not a mirror image, an isomer or non-chiral, would superimpose. Let me give you an example. I'm going to take something easy. Let's do Cl up, OH forward, or OH to the side, H forward, and H back. And so I'll get to copy this guy. So we've got OH, Cl, H back, and H forward. So now we're going to rotate this one 180 degrees so that the Cl and the OH are still there. OH is flat. But now, right, we've turned it. So this backwards H comes forward, and this forward H goes backwards. And what do we get? We get the exact same molecule. This will always happen if two of the groups are the same. There's always a way you can turn it so that it'll look just like the original and superimpose. That means if I stick this one on top of the other one, all of the hydrogens will be pointing and lining up in the same directions. So as long as there is two that are the same, we can still get mirror images, but they have to be non-superimposable mirror images for them to be stereoisomers. Okay, or at least to be enantiomers or stereomers. Another way of saying it is that they're going to be different molecules. They have to be different molecules if they have mirror images and are not superimposable. If they're superimposable, then they might just be the same image. All right. So again, this is another, just going into a better view of what I was showing you with that earlier example. The ethyl group is back, the ethyl group is forward. So these two molecules are functionally different from each other. You can see it here too. Hydrogen's sticking forward, and here it's sticking backwards. So objects that are non-superimposable on their mirror images are what we call chiral. And this comes from the Greek word care, which is hand. They show handedness. Okay, The most common cause of enantiomerism in organic molecules is the presence of carbon with 4 different groups bonded to it, as I mentioned earlier, and we'll call that carbon the stereocenter. Now, if an object and its mirror image are superimposable, then they are identical, and there's no possibility of enantiomerism. We say that a molecule like that would be achiral. And closer inspection of the molecule that I actually drew a picture of a stereocenter at, we see is not chiral, because this group has a CH3 and a CH3, 2 groups that are the same. So this would be an achiral molecule. But again, the stereocenter is going to be the carbon that has the multiple groups on it. And we can see just real quick another example of what I already showed you. I used 2 hydrogens. Here they're using 2 methyls. But you can see forward methyl, backwards hydrogen, forward methyl, backwards hydrogen. You can always end up with the same thing, even if you rotate it forward methyl, backwards hydrogen. This molecule is the same thing, right? These 2 are all the same molecule. But you shouldn't have to do the mirror image test to figure that out. You should be able to look at this carbon and say, that is achiral. There's no handedness. There's no stereocenter. Okay, so to summarize, objects that are non-superimposable on their mirror images are called chiral. The most common cause of chirality is a carbon with 4 different groups on it. A carbon with 4 different groups is called a stereocenter. Objects that do not have stereocenters are called achiral. Non-superimposable mirror images are called enantiomers. And enantiomers always come in pairs. That should make sense, right? Right hand, left hand. So, because enantiomers are different compounds, each must have a different name. So, here are the enantiomers of the over-the-counter drug ibuprofen. Now, you can see that they are, they're just mirror images of each other, but you can see the chiral carbon. I'm hoping you can spot it. This is the position of chirality. It's because the methyl is forward here and forward in the mirror image, that if we turned this guy around, it would be facing backwards. It would be pointed away and the hydrogen would be pointing forward, and that doesn't match with our with what we have on this side. So they would be different molecules. You could imagine a different molecule where the H is forward and the CH3 is backwards, and that would be the same one that we're looking at here. So this is a real thing that happens. There are positions where we can stick these atoms that are going to create 2 molecules that are mirror images of each other but are literally different from each other. Now their physical properties are going to be basically identical. They have the same boiling point, melting point, same reactivity, but they are just mirror images of each other. Now the way that we distinguish between these 2 different groups of the same molecule are with a system called the RS system. Now this RS system is a way to distinguish between enantiomers without having to draw them and to point to one or the other. So the first step in assigning a RS configuration is going to be to arrange the groups on the stereocenter in order of priority. Now here, they've already helped us. They've put the lowest priority object or item or group to the back, meaning all the other groups are either in plane or coming out at us. In plane, out at us. Okay? Now, to assign priority, this is based on atomic number. Of course, hydrogen will always go towards the back. I think I have a table. I do. So this is the priority. Now it's assigned by molar atomic mass, or essentially atomic number. The heavier elements have higher priority. So to give you an example, I think I have an example. Was I going to do it on the next page? I was, but I want to have this in front of us. So let me give you, so here are the two groups, CH2OH attached to a carbon, and here's another one, CH2CH2OH. So if these two groups are on a carbon, which one is going to have the highest priority? That's what we're doing here. We're just assigning priorities at the moment. So we look at each carbon and we see what it's attached to. If it's attached to something of a high, higher up on this list, then it has higher priority. If we get a tie, then we move on to the next one. So here, they're both attached to hydrogens. So tie. Then the next thing that the top one's attached to is an oxygen, where the bottom one has a carbon on it. So oxygen wins. So whoever gets a higher priority atom first, or you encounter it sooner, that's the higher priority. So here's the higher priority. Let's try another one. CH2CH2OH and CH2NH2. Should be easy. Nitrogen is higher up on, so you can use this table. Now this kind of helps down here. So you can see CH attached to an O is higher priority than a CH on an N or a CH with a C, which is what we get here. We get a tie between the N and the C, so higher priority. Okay, let's do another one. What about CH2OH and CH2C double bond O OH. So here it may look like this has a much bigger group on it, and so it should have a higher priority. In fact, when we're naming things, we look for usually the higher molar mass group, right? But in this case, we're just going to look at the atoms in their order of connection. So ties with the C. This one has a C, this one has an O, so higher priority. Let's do one like this. CH2NH2 and CH2C double bond O OH. So in this case, we get carbon and carbon attached to hydrogen and hydrogen, so it's a tie. Then it's a carbon attached to a nitrogen or a carbon attached to a carbon. So nitrogen wins. What if we kept going? What if this was CH2, CH2, even then, carbon, now this carbon here is attached to two hydrogens, whereas this carbon here is attached to 3 oxygens. I guess we could just look at the double bond. 2 oxygens. 2 oxygens trumps 2 hydrogens. So this would get priority. What about CH2C double bond O OH versus CH2C double bond OH? Carboxylic acid versus aldehyde. They tie with the C, ties with the C, C double bond O, C double bond O, but then an oxygen versus a hydrogen. So the next atom being an oxygen means higher priority. All right, what's the point of doing this, right? So let's just higher priority, higher priority, higher priority, higher priority. Well, the reason we do that is so that we could assign the letter R or the letter S to that chiral carbon. So once we've arranged our group from where we have the lowest priority towards the back, which is this rule right here, then we just read the 3 groups in order from 1 to 3. If that's clockwise, it's R. If it's counterclockwise, it's S. So let's try it. So here we have, now we've already got the hydrogen towards the back. So we just need to assign the priorities here. So we've got a carbon with an oxygen, a carbon with a carbon, or a carbon with a carbon. So here's our number 1. Now out of these bottom 2, we've got a carbon with 2 hydrogens and a carbon, or we have a carbon with 3 hydrogens. So I think the carbon with the extra carbon on it is going to be our number 2. And then that makes this the number 3. And so when we read this from 1, 2, 3, it's clockwise. So that's going to be R. So this would be R2-butanol. That's how we would name it. For alanine, this is an amino acid, same thing. We look at, what do we have first? It's carbon with carbon, carbon, and nitrogen, so that's the number 1. Then down here, out of the carbon-carbon, it's carbon with some hydrogens or carbon with some oxygens. So that's our number 2 and our number 3. And again, R. Let's do some more, or let's at least use this to prove that this is the case. So this is the 2 ibuprofens that we had before. Actually, we can go back to the ibuprofen and kind of figure it out here, so it's not shown. Okay, so hydrogens towards the back. So we've got carbon, carbon, carbon. Okay, so well, there's a tie, three-way tie. So we keep going. Carbon with hydrogens, carbon with oxygen, or carbon with carbon. This carbon here is double bonded to a carbon. That would be like a carbon with 2 bonds to carbon, as opposed to this carbon over here that has 2 bonds to oxygen. And just to show you what this group looks like, right? This is a C double bond O, OH. So this carbon literally has 3 oxygen bonds here. Over here, this carbon literally has 1, 2, 3 carbon bonds. So 3 bonds to carbon versus 3 bonds to oxygen, oxygen wins. So this is going to be our highest priority group. Now, out of the next 2 groups, we have carbon with hydrogen or carbon with carbon. So carbon with carbon is going to be the next priority. That gives the methyl the 3rd priority. And since hydrogen is always going to be last, it's the 4th. So then 1, 2, 3, clockwise, R. 1, 2, 3, counterclockwise, S. So that's how we decide S versus R in terms of the stereocenters or the configurations of a set of isomers here with only 1 chiral center. Now you can have more than 1 chiral center, which makes it even more complicated. So let's take a look. So sugars often have multiple stereocenters. For a molecule with N stereocenters, so N being the number of stereocenters, the maximum number of stereocenters is 2 to the N. So we've already verified that. For example, a molecule with only 1 stereocenter is 2 to the N, so 2 to the 1, or 2. That's how many possible isomers we have. 1 pair of enantiomers. Now, for a molecule with 2 stereocenters, a maximum of 2 to the 2, or 4 stereoisomers are possible, and with that we would get 2 pairs of enantiomers. So you can see here that this is a carbon that has 2 or a sugar that has 2 stereocenters. There's one here and one here, and as such, we can get. Let's see. We're gonna solve these on our own. Let's see. The H isn't pointed backwards with these, which always makes these less fun to do. But you can imagine, let's just say left, right, left, right. If this is R and this is R, then this would be S and this would be S, which would make this R and this S and this S and this R. So you can see already in the naming, we could call this one RR erythriose. We could call this one SS erythriose. And this would be SR threose, and this, or RS threose, and this would be SR threose, right? 2 different names for the same compound because they have 2 different stereocenters. Notice that we're going to end up with 2 sets of enantiomers, 2 sets of mirror images, but this introduces the diastereomers. Stereomers. All right, Diastereomers are stereoisomers that are not mirror images. So for example, this guy, while he is a mirror image with his enantiomer buddy, he's a diastereomer with both of these because they are stereoisomers, but they are not mirror images of each other. So we have two sets of enantiomers. We get a set for every for every chiral carbon we have, but all of the other relationships between the isomers are called diastereomers. All right. I want you guys to mark all the diastereomers or all the possible stereocenters and tell me how many stereoisomers would be possible. So go ahead and pause the video, and then I'll give you the answer. So 2 to the 1 equals 2. 2 to the 1 equals 2. Don't forget about the hydrogens that are hidden back there. All these line angle structures, right? We don't always show the hydrogens. On symmetrical rings, you wouldn't have two groups. If the OH was here, then the carbon connectivity this direction is the exact same as the carbon connectivity this direction, and that wouldn't be a stereoisomer. But because this OH is off-centered from this group right here, this direction from the carbon is different from this direction from the carbon, and so we do end up with a stereocenter. This guy and this guy, or 4. All right. So if you got all that correct, then good. You need to pay attention to, again, the fact that there are hydrogens still not shown on a lot of those carbons. Okay, so those are where all your groups are. The OH, this part of the ring, the down, and then the hydrogen. Okay. Let's look at a scary molecule. So this is cholesterol. The 2 to the n rule applies here as well with more than with 3 or more stereoisomers. You can see cholesterol has 8 stereocenters, so there's 256 possible stereoisomers. This is the one out of the 256 that we find in our metabolism. So that means there's all of those different molecules where these groups are flipped, so like this position here, right, where the hydrogen is back and the methyl's forward. That wouldn't be a cholesterol molecule that your body wants. Now let's talk about optical activity. There is some effects of ordinary light. Now light brings in light waves that are vibrating in all planes perpendicular to the direction of propagation. So what that means is if there is some photons flying this way from a light source, okay, the oscillations are happening in an up-down sort of way, but they're also happening in an in-out sort of way, and every way in between. Okay, ordinary light does that. The vibrating waves, they go in all directions that are in perpendicular to propagation as well. Now, plane polarized light is something a little different. Now, these are light waves that are vibrating only in parallel planes. So we get, it's almost getting laser-like, where the light is only moving in parallel planes. So they will never intersect with each other. The plane this way is right next to this one, right next to this one. And that's different than what we get for ordinary light. Now, a polarimeter is an instrument that measures the ability of a compound to rotate the plane of polarized light. And I think I actually have an image you can look at. And so when we say that a compound is optically active, it means that a compound is capable of rotating the plane of polarized light. So let's say that light is coming in from its source, of course, in all different polarizations. we orient the light for our device to only come in through a filter in a 180-degree angle. So it's up and down light only. We've eliminated the left and right light. This is what your sunglasses do anyways when they're polarized sunglasses to reduce glare. They have little etched lines in them that don't let light through in one of the directions. So if that light stays that direction the whole path through the sample and comes out 180-degree light, then it wouldn't be optically active. But if that light gets turned somehow, and so you can see this light's coming out at a different angle than 180, then that means it was optically active. And it has something to do with the way the light interacts with enantiomers. So let's talk a little bit about the differences here. So we say that light is, that a sample is dextro rotary if it will rotate the plane of polarized light clockwise. We say it's dextro rotary, we say it's positive, this is all clockwise. We say that a sample is levorotary if it goes counterclockwise, if it makes the light turn the other way. Now, the specific rotation given by, let's say, readings like this, are the observed rotation of an optically active substance at a concentration of 1 gram per milliliter in a sample tube that's 10 centimeters long. So specifically, we can set up tables that will give us this information. So you can see these are enantiomers of lactic acid. One is the S version, and one is the R version. Now S here tells us how to draw it so that we can put the groups in the right orientation, but it's dextrorotary, so it rotates light to the right or clockwise. That's different than how we said if the groups were oriented in a clockwise way from priority, from greatest to least priority, that's what we called R. So R and S here have nothing to do with plus or minus in terms of the optical rotation. But you can see here we can also get that angle at which that light gets rotated by. All right, now except for inorganic salts and a few low molecular weight organic substances, the molecules in living systems, both plant and animal, are chiral. So although these molecules can exist as a number of stereoisomers, most invariably only one stereoisomer is typically found in nature. Instances do occur in which more than one stereoisomer are found, but these are rare, especially in the same biological system. We have enzymes that are actually really capable of distinguishing between a molecule and its enantiomer. And so what I'm showing you here is a schematic diagram of an enzyme surface. And it can actually interact with the R glyceraldehyde at 3 binding sites. So it's got the spot for the aldehyde group, for the hydrogen, and for the hydroxyl. But the S glyceraldehyde would only interact at 2 sites, the hydroxyl and the hydrogen, but it wouldn't have a spot for this now methoxy group. And so that is how enzymes are actually really capable of discerning between biologically active enantiomers and the ones that don't do anything. Enzymes, almost all of them have stereocenters. A good example would be chymotrypsin. It's an enzyme in the intestines of animals that catalyzes the digestion of proteins. Chymotrypsin has 251 stereocenters. The maximum number of stereocenters possible then is 200, or the stereoisomers is 251, or 2 to the 251, right? That's insane. One of these stereoisomers is produced and used by any given organism, only one. We're talking about chymotrypsin. So because enzymes are chiral substances, most either produce or react with only one substance that matches their stereochemical requirements. So again, we can have molecules that are stereoisomers that will only interact with enzymes if the enzyme is the right one. But also enzymes themselves have so many various sort of configurations that your body can get very specific, right? Think about it. Every one of these enzymes might have a different molecule and only one molecule that it interacts with. So because Interactions between molecules in living systems take place in a chiral environment. A molecule and its enantiomer, or even one of its diastereomers, will give different physiological responses. There's a good example it was a morning sickness medication, excuse me, that they don't use anymore because when you made it, it came in two enantiomers. You couldn't separate them from each other because it's hard to do that. They have the same physical properties. And one of these enantiomers would relieve morning sickness, while the other one would cause some terrible thing to happen, and you would abort the baby, so or miscarriage the baby. So they had to stop using that altogether. Right, two completely different effects from the same molecule, essentially. And so as we've seen S-ibuprofen earlier, this is actually used in pain reliever and fever reducing, while this R version of ibuprofen is inactive. The R enantiomer doesn't do anything. The S enantiomer of naproxen is the active pain reliever, but the R enantiomer is actually a liver toxin. So we need to be very careful as scientists when we make something and be able to tell if, and here's the thing, a compound that has equal parts, S and R, when you put it into solution, it won't be optically active at all, because the S enantiomer curves light one way, while the R bends it back the other way. And so mixtures of these compounds will lead to an optically inactive compound. And so we need to be good at figuring out which enantiomer we're dealing with and which enantiomer is deadly, and so on and so forth with the chirality of molecules. But as far as for what we're doing, we're just looking at that chirality exists, that molecules come in these different types of isomers, these diastereomers and enantiomers that you didn't know about before, and how to go about just assigning R and S to those. Okay, we'll continue talking about R and S as we get to the carbohydrates and amino acid chapters later on. But for now, that'll do it just about for the chirality chapter. All right, guys. So I will see you in the next video, and send me your questions.